Whenever I talk about astrobiology and the search for life in the universe, I get a lot of comments on my videos saying that scientists are just so anthropocentric. They're thinking about life as we know it. Well, what about thinking about life as we don't know it? Why aren't scientists doing that? Well, of course they are. They are looking for and imagining ways that life could be and form out of different chemicals that we understand, use different solvents, and maybe evolve into different kinds of life forms. And then what kind of after effects, what kinds of minerals should we expect to see? What kinds of gases should we expect to see produced in the universe? And one person who's been thinking a lot about this is today's guest, Dr. Chris Impey. He is a distinguished professor of astronomy at the University of Arizona. He is a well-known science communicator and professor and educator. And he recently wrote a really fascinating article on The Conversation about how astrobiologists are thinking about the search for life as we don't know it. So enjoy this conversation with Dr. Chris Impey. All right, Chris, I've got your hard question first, just to get this all out of the way. What definition of life do you like the best right now?
Oh, wow. I mean, I'm not a biologist, so I'm not even qualified to answer the question, which I guess means I can say anything.
Yeah, perfect. There's no rules here.
I'd say, a complex autocatalytic chemical network that has the ability to increase in complexity and evolve in that sense, in the time-ordered sense, and also that has molecular components that store and transmit information. I mean, that's kind of clunky.
Yeah, we need to workshop it. What's the short of the elevator pitch? No, I think that's great.
As you know, the dichotomy in this field is that the most hyper-specific definition of life that accrues to our form of biology does not help you when you're looking for life elsewhere. Mm-hmm. And then the most very general form of the definition that doesn't invoke any biological or chemical terms at all, it just talks about organization or structure or information, it's not very helpful. It's not prescriptive enough to be helpful. So the two extremes of the definition are not useful. And in the middle, it's a muddy mess and nobody agrees.
Yeah. I mean, it's funny. It's like, you want to be able to know it when you see it, but you also need some way to imagine ways to see it if you don't know it. Like you need to be able to think out of the box and open up your mind to other possibilities to see things that maybe aren't falling into these very strict guidelines. And I'm sure that's half the fun is people just going back and forth with their definitions of what is life. Now this interview is sort of stemming from a really interesting article that you put together for The Conversation, just about sort of how you think the search for life could progress in the future. And one of the concepts that you put into this was this idea of information storage as it relates to life. Can you sort of expand upon that? What does that mean?
Well, so genetic information is the key to life. So there has to be information that describes an organism and its function and form, and we know that is encoded in the DNA, in RNA or the DNA, and the genome of any organism, is the sum of all that information. And the information is, of course, we don't know how to parse all that information. Genomes have been parsed, but we don't know how to unpack the information that exists in the 3 billion base pairs, say, of the human genome, because some of it's still mysterious. We don't know what it does. But that's the general idea. The carbon is a fabulous element for creating infinitely long molecules, and DNA and RNA are, very clever molecules that allow for the transmission of information when they split and then reproduce with some error. And the error is important too, because, if replication was perfect, then life wouldn't evolve.
I'm going to be sprinkling in. I told my patrons that I was going to be interviewing you today, and they had a bunch of questions for you, and I'll be sprinkling some of them in as they seem relevant to the conversation. This one comes from James Green. Earth life is based on DNA with 4 MERS. could life exist with different MERS than Earth DNA? 6, 8, 2?
Oh, absolutely. And there are people. Steve Benner is a iconic figure in this field. He's a physical chemist, but he works in the biology space too. And he was the first person, I think, almost 20 years ago that swapped out base pairs or added a base pair. So he expanded the alphabet of life in the lab, and just showed that you could create stable information bearing molecules that were not exactly the one that happened on Earth.
Now, you also talk about this idea of there being broader evolutionary laws that could define sort of how life evolves. And I guess, Earth life as we understand it is sort of a subset of that broader evolutionary law. Are there like first principles? Like if you go down to like the quantum mechanical level, to the physics level, the chemistry level, and then build up from there, do you think there's like a general set of evolutionary laws that could be derived?
It's an interesting question of whether it happens at the core physics level, but I don't think so, because quantum mechanics is pretty resolute. It's time reversible. Schrodinger's equation is time reversible. And so the fundamental building blocks of quantum theory don't have a time arrow or anything that would imply evolution, and they don't really speak to complexity at all. So it's only when you get into chemistry that you have the possibility in a liquid medium that chemicals, just the way in the nature of bonding, that you'll get more and more complex chemicals over time. So you can have chemical evolution. And then Bob Hazen and others have shown that you can have mineral evolution too. So once you get to the level of a planet and liquid medium and dynamism caused by volcanism and other things, then you'll start with a very modest set of minerals, primordial minerals on the early Earth, maybe a few dozen, and then it grows steadily with life and in a sort of symbiotic way with biology, because biology, of course, uses the materials around it and repurposes them and creates new ones. So mineral evolution on Earth has tracked biological evolution to the point where we now have about 3,000 different mineral species on our planet. And that would not have been the case if it wasn't a living planet.
Right. That a large percentage of the minerals that we find here on the surface of Earth are produced by life or as an output of life.
Right.
And like you suggest that is another type of biosignature, but I sort of think about the difficulty of us even detecting the really simple chemicals like oxygen, ozone, methane, and stuff from these vast distances to other star systems. Do you think that there will come a time where we can practically look for this mineral complexity as a potential biosignature?
I don't think that'll happen. And if we had the technology to do that, we would be seeing other things that would be a little more direct. So basically, we're asking, can we isolate the light from an exoplanet, Earth-like exoplanet, spread it into a spectrum? And that's what we're going to do to look at the atmosphere. But if we could do surface reflectance spectroscopy, then yes, maybe we could even diagnose the complexity of minerals on the surface. But if we had that level of information and data, we'd also be looking at whether it had continents and oceans, and possibly whether it had, giant industrial civilizations covering the surface. So to get to that point, we'd be in a new regime. And those observations at that level of detail of an Earth-like exoplanet, even the nearest ones, are decades away. We don't have any instruments that could possibly do that.
But here in the solar system, if we can directly sample things with our rovers and so on, that becomes a lot more possible.
Right. And as always, the exciting object in the solar system to me and many planetary scientists is Titan, because if you do want to find a different version of life, you would go to that alien environment where there is a lot of dynamism, there's cryovolcanism, there are liquid bodies which are made of ethane and methane with a little ammonia and a little water mixed in. So the biochemistry, if it evolved on Titan, would have to be very different from terrestrial.
I mean, the question that I get a lot from people is, astrobiologists, we're so anthropocentric. We're always thinking about life as we know it, and I always describe that as the low-hanging fruit. Like we haven't really even very thoroughly searched for life as we know it, not to mention life as we don't know, which sort of by definition falls outside our understanding of what life is or could be. Do you think that's starting to shift?
It's starting to shift, but it's a ugly pragmatic issue of how you design an experiment. So, NASA's kind of painted into a box, say, when it designs rovers or missions to Mars, just because Mars is the low-hanging fruit, because it's the closest object that might have had life and might still have life underground. So if you design, and there has been no true life detection experiment on Mars yet. The rovers are not doing that. But there are plans for that. And so what do? You definitely could design instruments, and we've tested them on the Earth, that could test for nucleic acids, and this, in a very prescriptive way, look for our formal biochemistry. But then they'd miss, something that was different, that wasn't based on nucleic acids, or wasn't in the metabolism like a terrestrial metabolism. And so when you're spending, $1 billion or so on an experiment, you have to find an answer. And so you have to ask a question where the question gets answered. And so naturally that makes you conservative. You look for life as we know it and as prescriptively as we know it, so that you can answer the question and say, no, we didn't find that on Mars. That's not what's happening on Mars. And then you have the definitional problem that if you're not looking for that, how do you design an experiment to test for life as we don't know it? And that's an unanswered question. Nobody knows.
I mean, there's a lot of interesting thinking on that. Partly what you were describing here, that you look at maybe the mineral complexity as the outputs. Like if you're seeing minerals that we just don't have on Earth, then maybe they're the result of the output of novel life forms. And I know other people are thinking about even just grinding up samples of material, and then if you find a higher prevalence of more complicated organic molecules, that is a tendency towards suggesting that maybe you are looking at some kind of life. But you talk about this idea of evolutionary, like, information density actually starting to decrease as life forms become more evolved. Does that sort of run counter? Does that make it more complicated?
There's a little counterintuitive thing going on. And so if you want to piss off a microbiologist, just tell them the bacteria are simple. That's the easiest way to get an argument out of a microbiologist.
The way to troll biologists is just tell them bacteria are simple.
I've had my hand slapped in the past, so I don't do that anymore. So what happened and then this is all bracketed by the fact that we don't know how life on Earth started. So we're not even dealing with a totally known and understood issue of how life started on the Earth to then go and look for versions of that elsewhere. And that's a terrible asterisk against the research, because if you don't know the path by which simple chemicals turned into the first cell, then how are you supposed to project that into a different physical environment, different chemical environment? But what appears to be the case is that that is the critical. Those are the critical dots that we haven't yet connected to get to the first cell. And the very first cells, the first early bacteria or archaea, the most ancient bacteria might have been in a deep sea hydrothermal vent or deep in rock, probably not on the surface or in Darwin's shallow little pond. They were pretty complex. I mean, they coded a lot of information. They were very complex chemical factories, with many moving parts and many components. And then things became modular. So it took a long time on Earth to go from single cells to multicellular organisms. But that's not a dramatic change in complexity, actually. It just allows you to differentiate function. And so humans are made of 50 different cell types. And so brain cells and liver cells and bone cells do different things. But that's not, so putting cells together into multicellular organisms is not a dramatic step of complexity or information storage, nor is going to larger creatures, going from microbes, multicellular microbe colonies, to plants and animals, say, which only happened in the last 500 million years. So, and then in just simple numerical terms, it's always amusing to me that if if you looked up on Wikipedia, whatever, what's the largest genome or the largest few genomes, they're nematodes or plants, or, they're not what you would expect, or something like a worm, I think, is the current record holder. And we're talking about a genome that's 5 or 6 times the human genome. And so clearly it's not a numbers game in that level. It's not as simple as that. So complexity appeared to rise dramatically in the creation of the first cells. And then it has increased since then, but not dramatically. And then there are these counterexamples, very large genomes on what we would think as simple organisms and so on.
That's really interesting. I think of an analogy like my work with programming, that when back in the olden days, we would just sort of write all the spaghetti code to get the job done. Then after a while, we started to have object-oriented programming. We'd have classes and functions and ways to break up the problem into pieces and have them do their own separate little piece. And things became conceptually simpler so that we could develop more complicated applications.
Right.
And so we have broken up, like my liver cells are not very robust. They can't live on their own. They can only, as long as they get the inputs and the outputs they require, then they can do their job and they do it well, but they're not the whole package the way a bacterium is.
Right. And the other problem is we use these very simple and misleading metrics. So just talking about number of base pairs or the size of the genome or the number of genes as a measure of complexity and sophistication, if you want to use that word, is inappropriate. If you want to piss off a general biologist, talk about junk DNA, because we haven't in any genome, our own or any of the others that have been parsed, we don't know the function of all the components in the DNA. We don't know what the billions of base pairs do. There are coding sequences that we clearly know, and then there's a bunch that we didn't. And they used to be called junk DNA. It was a pejorative, silly term, and it's clearly not true. And so the current view is that our genetic material is it's an archaeological experiment. It's a compilation of all the mistakes and false paths and things and innovations that worked for a while and then were not useful, or redundancy. There's also, of course, redundancy. You need that anyway. And so you can't there's no simple metric for measuring complexity, true biological complexity. They're all misleading at some level.
So, I sort of think of an analogy again, like when I think about, say, the Big Bang, we see that the universe is less dense today, which means that it was more dense in the past. And we can sort of calculate this time when the universe was so dense that it was like the core of a star. And then it was like some point where these forces were starting to come together in these fundamental ways, if you sort of run time in reverse. And so if we sort of look at the process of evolution, if we are less complicated, but then bacteria are more complicated in terms of information density, does that mean that whatever was the first life form started at an even higher information density and came down to bacteria, or that it was sort of like an up and then like it ramped up and then has been going down?
I think the trouble is we don't really know, because there's still no issue of, people think maybe before conventional cells there was RNA world, and then some people say no, well, RNA was important and it's still important, but they like more the idea of metabolism first as opposed to RNA first. And so you just have some set of metabolic network forming in a liquid medium where there's a lot of complexity there, and eventually at some point a container forms and concentrates that complexity, and we don't know how that happened. So there's really just too much ignorance over how you get to the first cell to draw any graph or a trajectory of complexity. I think nobody knows, actually, and it's not unreasonable that there are false starts, or that it's what Darwin didn't say this, but he might have. Life is just sort of good enough. It doesn't have to be perfect. It doesn't have to be an optimum solution to anything, because if it's too optimized, then of course it's not robust enough to change in evolution and the wild cards that the universe throws at planets, like giant impacts or catastrophic climate change or whatever.
I got sort of a related question from billions and billions of stars. What biological markers would be present on an exoplanet with silicon life forms?
Well, it sort of depends on how those silicon life forms metabolize. The larger statement, which I've read enough of what the chemists have said, is they're pretty pessimistic about silicon-based life. In the periodic table, it would seem to be amenable to forming large complex molecules, but they're far less stable. So once you get into the actual chemistry you can do based on silicon, it's not as robust, it's not as stable, it's not as diverse, and so it's if nature's going to choose one path, it's unlikely to be the silicon path, even though silicon's a very abundant element. That's another reason you might suspect to look for it. But if you're looking for the biomarker associated with silicon life, it'll again be based on a sort of metabolic byproduct, just like the oxygen that we still think of as a classic biomarker was produced by cyanobacteria 3 billion years ago, starting 3 billion years ago. So there'd be some analog of that for silicon-based life, but it wouldn't actually be the silicon itself that you're looking at. It would just be compounds, silicon-based compounds that have been used to extract energy from their environment, and they released a waste product, say, like oxygen or methane or something like that. Methane's also a good biomarker.
Right. But like back to your original sort of comment about the complexity of the mineral deposits on Earth, that we're seeing the waste products of carbon-based life, but there would be like a different set of minerals as the waste particles of a silicon-based life.
Right. And it's an interesting thought experiment. Unfortunately, it's very difficult. It's very difficult to simulate that and make a prediction. So I don't think anyone's done that. I mean, the biochemists have explored the potential for silicon-based life at the level of very basic biochemistry and chemical networks and what do you get, but not at the level of like an ecosystem based on silicon-based life and what the inputs and outputs and the energy balance and the waste products. That's nobody's done that. I don't even think we know enough to do that in a computer.
Yeah. I mean, it's interesting. I sort of think back to like these evolutionary like simulations that you make where you create some life form and then you release a whole bunch of them and then you watch them evolve and you put pressure on them and they, almost like via neural networks gain these skills and abilities. But if you go one level down and simulate, I don't know, like I know there's like the virtual worm project where people have simulated some kind of nematode and you can actually like run this thing in a computer. That's the level of granularity that you have to be able to achieve if you want to get any kind of reasonable answer to your question.
Right. And I think the big issue, which is good, I mean, it makes it a rich subject, is that this interplay between, instead of thinking of life as being painted on the surface of a planet, it's highly interacting. It's interacting at a very deep level with the planet itself, with the atmosphere and the surface and even the subsurface. And so those interrelationships are critical. I mean, and so that means you have to know that much about the physical environment of the planet, as opposed to just, looking at the biology itself in the lab and have a cell in the lab and look at how it works and what it's made of. That's not going to tell you enough. It's not going to tell you everything you need to know. So the interplay between biology and geology is really critical to that. And that's what, of course, the mineral evolution thing is about. And that's why, you can go back to James Lovelock and his Gaia hypothesis. And, he was hired in the 1970s, I think, when they were starting to do Mars missions. And he was kind of a radical thinker. And he said, well, you're wasting your time. Mars has carbon dioxide atmosphere, very thin. It's dynamically uninteresting. No active volcanism, thin atmosphere with carbon dioxide. That to him just said a dead planet. And the Earth said, a dynamically active planet. So he said, you're wasting your time. You can just tell by geology and atmospheric chemistry whether there's likely to be life on the planet. So it's going beyond saying a biomarker, which is a telltale for life. He's saying you can also look at a planet and say, almost certainly no life as we understand it, or maybe in any sense because of the dynamism that's part of biology. So if it's really static, then that would speak to no biology of any kind.
But he went further than that. I mean, he was talking about that life serves as a mediating, moderating role that is deeply entwined with those natural processes, and even helps to bring them back into some level of homeostasis.
Right. He was very careful not to push the sort of new agey interpretations of the Gaia hypothesis, but that's okay. People took it and ran with it anyway.
Yeah.
But yeah, he was pointing to a sort of thermostatic mechanisms of the Earth, and that goes to the faint early sun paradox, that you have when you run climate models, because the sun's changed its luminosity quite substantially, and the biology has evolved to adapt to that pretty dramatic change in the source of its energy. And so he outlined these kind of coupled mechanisms of biology and geology that were self-correcting and thermostatic in a sense, rather than the opposite way of a runaway effect. He didn't impute anything larger to that. There's no teleology in there, which is good. He didn't go there. Other people did. But that's interesting. Does that always happen? Or do you have more situations, say greenhouse effect, say Venus was a living planet 3 billion years ago, and the thermostat didn't work. They got the worst case runaway greenhouse effect.
Yeah, although there's papers now that just came out within the last couple of weeks saying, based on the dryness of the interior of Venus, maybe it was never hospitable, never had water on its surface.
Right. Yeah.
And that would be another piece of evidence that it was always dead.
Yeah. But again, if you just looked at it as a planet within 5% of the mass of the Earth, and somewhat hotter, but not dramatically hotter until what happened in the last billion years or so, you wouldn't, if you were looking at Venus and Earth and Mars in a distant solar system, you'd be interested in Venus, in that distant Venus for sure, based on its physical properties.
And this kind of relates to a question I got from Levi Osborne. What evolutionary pressures might super Earths put on life in these types of planets? So
super Earths, to some astrobiologists, are more habitable than Earth-like planets. That's a dangerous thing to say. It's fallacious to sit on the Earth as a living planet and say it's the best of all possible worlds. It's almost certainly not. So super Earths, the larger gravity is not an issue for life, really. Especially since so many aspects of life are in the water, and so there's buoyancy there. The super Earths are there's a very strong implication, because you need this sort of geological dynamism, that you need plate tectonics or the kind of things that lead to deep sea thermal vents and so on. And super Earths are going to be geologically very dynamic, maybe almost too dynamic, but they're going to be very active. And so, they just have some of the dials are twisted in the right direction for a super Earth. And there's no particular downside that goes with being a few times larger than the Earth.
Until they try to figure out rocketry.
Right. Yes, exactly. So Elon Musk would be earthbound if he lived on super Earth.
I always think that would be so sad, that we would travel the Milky Way and we'd find some civilization that is on, say, 5Gs, and they're doing fine. They live in the water, and they have technology, and they move around, and they communicate, and they say, "Could you give us a lift?" And we're like, "Absolutely not. There's no way we're coming down into that gravity well."
Right. And that's a little anthropocentric too, because we're stuck. 100 years after Robert Goddard's first rocket, we're still stuck with chemical energy. It's great. Elon Musk's Starship is bigger than a skyscraper and really impressive rocket. It's just a cousin of Goddard's little rocket. So until we get away from our archaic chemical fuels, we would be stuck on a super Earth.
So this idea of anthropocentrism, that, we're thinking about chemical rockets versus, the obvious antimatter rockets that we're going to have in the future. I'm really interested in now our search for technosignatures, that we're starting to think about how we will evolve as a civilization into the future, and the kind of impact we're going to have on maybe our planet, our solar system, maybe even our galaxy, and then we can say, well, let's look for examples of that, because it gives you this really clear cut, unambiguous signal that, okay, something interesting. You see a Dyson sphere, then that tells you that that's a biosignature as well. But again, back to that idea of us being very anthropocentric. How can we think about technosignatures in a more non-biased way about like all the possibilities?
I think that's probably even harder than the biology. I mean, it's interesting, just to go back to biosignatures and the crossover. It's nice that the same technology that will let us inspect the atmospheres of Earth-like planets, with James Webb and with the big new ground-based telescopes, and look for oxygen and methane and a suite of biomarkers, will also let us detect nitrous oxide, which on the Earth was a product of industrial activity, and it doesn't occur. You can't get nitrous oxide at a substantial level naturally, and so nitrous oxide is a technosignature, which would come from the same observations that you'd use to detect just simple microbes on another planet. So that's interesting, but it's again it's in our case a few hundred years of industrial activity. So it's this little narrow window, highly tied to our particular evolution through a dirty industrial phase before we became all clean and renewable. Hopefully we're not there. But, and so when you go to the usual problem of mismatch of timing, that if you're talking about civilizations that have developed technologies, we're in a moving window of technologies. So SETI is used radio and optical methods and so on. But, if you're 1,000 years more advanced, you'd probably be using gravity waves to communicate, because they travel much more efficiently through space. They don't take a lot of energy to generate, and you can code information in them. And it's a much smarter way to communicate. So, and so for the technosignatures, it's just, again, what you don't know what to look for. And if you took our current path of miniaturizing technology, then you would probably decide that the technosignatures will be imperceptible or unrecognizable or just too subtle to recognize. They're not necessarily going to be Dyson spheres at all. They could be at the absolute opposite end of that. They could be just hyper miniaturized networked devices or semi-sentient or sentient devices that from a distance there's no conceivable way you'd ever detect them.
I mean, that sort of feeds into this idea of the sustainability as an answer to the Fermi paradox, that if any civilization that is dependent on growth is limited to eventually gobble up its environment, depending on how big it considers its environment to be, and there's a quote in this paper that I really liked. It was like, any sufficiently advanced civilization is indistinguishable from nature. That only
magic. Arthur C.
Yeah, exactly. It was a take on the Arthur C. Clarke one, and I thought it was great, because it's sort of like, if you want to be around for 1 billion years, you've got to figure out a way to live in harmony with the natural world as we find it.
So we're voracious consumers of energy, and we do it very inefficiently, and we do it in an archaic way, and it's just implausible to imagine that more advanced species would operate that way, and they would run into the limit of their resources. So there's very good reason for them not to do that. So this is presumably just a teething phase of a civilization as it grows, and we can't even say there'll be analogous teething phases of other civilizations that we could look for, although that's a premise of even looking, I think, for technosignatures. But yes, the sort of end game, the long game of a technological civilization would be to be in balance with its natural resources at some level, because otherwise it's not sustainable. And then just it's such an anthropocentric idea, the idea of growth above all, that growth is what matters. Just like with biology, the idea that bigger is better, a bigger organism is better than a smaller organism. Well, we know in many ways that's not necessarily true.
Right.
In terms of
and now apparently less complex.
Yeah.
So, and I got a related question from Rad Gentle. If Earth is the only life-sustaining planet in the galaxy, do you think humanity has an ethical responsibility to spread life beyond Earth?
It's a good question. I mean, that's a huge if. At this point, I mean, most astronomers and astrobiologists, of course, are very loath to recognize the Earth as the only living planet in the galaxy, because there's just such a vast amount of habitable real estate. You're asking for 30 billion Earth-like worlds that have all the ingredients and plenty of time, including billions of years before the Earth even formed. So their timeline is 12 billion years, possibly, for there to be no biological experiments on any of the others of them. So that seems implausible. But even if it were the case, if we're unique, I don't know. I don't think you can do ethics based on a sample of one, just as you can't do science based on a sample of one. So I think I could make a plausible argument the way the questioner framed it, or I could make the opposite argument.
That you either, obviously we're colonizing just dead rocks and trees are better than rocks, or we are potentially filling the galaxy with invasive species, and it's just a matter of time before we find out what their harm is on the indigenous life forms.
Right. And, at some root level, these are all value judgments, and the universe doesn't care. The galaxy doesn't care. The dead rocks don't care whether they're dead or alive at a non-sentient level, at least. Yeah, there are astrobiologists like Chris McKay who said, it's our obligation. We should get life on Mars. We should plant a flower on Mars, and just to show that we can do it. Okay, maybe.
Yeah.
I mean, NASA's, to its credit, taken seriously the contamination issue forward and backward, and they're trying to do their best not to mess Mars up, contaminate it with future missions and with even previous missions. And that's a philosophy that they will follow in the outer solar system too. And I think that's good. That's just a cautionary principle that you should follow.
I hope you enjoyed that conversation with Dr. Chris Impey. Now, one of the other tasks that Chris is involved in is trying to formulate some kind of message that could be sent to extraterrestrial civilizations. And so I had a much larger conversation with Chris about what it's going to take for us to be able to craft a message to another civilization. What are the risks? What are the philosophical, ethical implications of that? And then kind of more deeply, what if we get a message? Should we even open it? Can we stop ourselves from opening it? Now, this additional bonus conversation is available over on Patreon. It's available for free, so you don't have to give us any money. You can just follow us on Patreon and get access to that additional interview. I'll put a link here, and I'll put a link in the show notes, and hopefully you'll enjoy that. It was really fascinating to continue that conversation. Chris, what are you obsessed with right now?
Well, I mean, in that we're talking about it, I'm obsessed by the question of life in the universe, because it's been so abstract and hypothetical for so long, and now finally the tools are on the horizon to do the experiment. SETI is just a side bet, and who knows, it's a great silence for 60 years. It could be a great silence for another 60 years, even though our messaging, the power of our receivers and transmitters is increasing steadily. But the fact that we are really just a few years away from sniffing atmospheres of Earth-like planets for biomarkers, and you'll never know from one. The data will be ratty, and there are no slam dunks here. It's not going to be a news headline on day one. But once you've built a sample of 20 or 30 or 40, you're going to be statistically answering a very important question. I mean, if you find nothing that of our recognizable biology in the first 20 or 30 instances of a truly Earth-like planet where all the ingredients are there, liquid water's there, etc., that's probably telling us something. So that's exciting. And I just am happy to see astrobiology maturing so fast that that the core question that sits behind the whole subject is upon us. And then we're going to answer that question probably long before we answer the question of how did life actually start on Earth, because that's that's a crime scene where all the evidence has been destroyed and trampled and overwritten and lost billions of years ago. So that's a historical question that we may never be able to answer. Whereas the outward-looking question is one we can build telescopes and design instruments to answer as well as we can.
It's interesting, like with this next round, when we get to say the Habitable Worlds Observatory, then there is this sphere around the Earth that we can fairly conclusively explore with our telescopes to figure out what is the sample rate of how many of those planets out there have life. And if the answer turns out to be 0, then we build the HWO2, which has an even larger aperture, is more capable of these kinds of things, and it expands out that bubble of what we can detect. If that, and then eventually we build the solar gravitational lens, we have the Habitable Worlds Observatory out there, and we're seeing megapixel resolution of these planets, and we're mapping their continents and so on. Once it becomes this very measurable result, and as the sphere of non-detection expands, when do you think we have to start wrestling with that possibility that we're alone in the universe?
I think that could be upon us within a couple of decades with the progression you described, because it doesn't mean we're unique, but it's statistically going to be a pretty strong result if you get up to the level of dozens, where there's no reason for there not to be a biological experiment as we understand it. And then that's not even worrying about life as we don't know it. And we'll probably get some tools that will help us look for variations on, silicon-based life or Titan-type life or some other plausible variations on biochemistry, and maybe we'll start looking for those. I don't know why it should be uncomfortable for people to think that life on Earth was a fluke. That's almost a value judgment too. Does that demean us or diminish us in any way? That we're just an inconsequential contingency in a fluke biological experiment that started 4 billion years ago? Does that make people feel bad about their place in the universe? I don't know. I haven't asked enough people that question, but I have a feeling it does. I have a feeling the urge, the desire for companionship writ large is pretty strong. It's built into people because we're social, we're tribal. We would like to be part of a tribe that goes beyond this rock.
Right. And so I guess that philosophy is anthropocentric again, which is, the way we think about our place in a unpopulated or populated universe comes back to our basic human values.
Yeah. And then, and does it, can we live without it? We should, if we're highly evolved species, which we're clearly not, we should sort of be beyond that. We shouldn't be necessary. It's almost like a crutch to have your validation based on whether you're unique or part of a, biological universe where there are all these other examples. And then you can feel superior to them because you find out they're almost all microbial and none of them, given billions of years, never evolved past single cells. And you go, oh, nice,
Yeah. Except we know that they are, more complicated, more sophisticated, more highly evolved life forms. And so really we should feel secondary to them. Well, Chris, it was a fascinating conversation. I really appreciate you taking the time to chat with me today. Good luck with your research. It's a pretty exciting time to be thinking about these kinds of ideas.
It is a lot on the horizon. Yeah, it's fun.
All right, take care.
Thanks, Fraser. Good to talk to you.
I'm going to share some resources here on the channel, but first I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew Gross, Bear Lake Roofing, David Gilton, and David Matz, Dennis Alberti, Dustin Cable, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, Spiderswap.io, Stephen Fowler Munley, and Vlad Chiplin, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. Now, this idea of searching for biosignatures, searching for technosignatures, advanced techniques for different telescopes that are coming up, thinking about the life forms, solvents. I have interviewed many people across all of these fields, and so I'm going to put a bunch of video links here so you can follow these conversations more. Two that I think would be really interesting. One interview that I think you'll really like is this conversation that I had with William Baines. He's a chemist and thinking about different kinds of solvents that life could use, not just water? What if life could use sulfuric acid or liquid methane or things like that? And what would be the implications of that? And the other interview that I think you'll find really interesting is with Dr. David Kipping. Now, obviously from Cool Worlds fame, and he thinks a lot about both finding exomoons, but also finding other life in the universe and really the search for technosignatures. And so I'm going to link to the most recent interview that I had with Dr. David Kipping. All right, I hope you enjoyed these interviews. We'll see you next time.